Alright, so let's go through some examples. We'll start by just writing some algorithms out in pseudocode, and then we'll look at what's the total running time, and then we'll look at the asymptotic running time. So first, let's just start by writing an algorithm that searches an array for a given number. So we'll have a function, and let's just call it the find num function. And let's say that that function takes two variables. So we said it takes an array because we're going to search in an array, and it's going to search for a given number, so we have to pass in a number that we're searching for. Alright, so there's our function definition. Pause the video here and write out this function. So we're going to search an array for a given number, and let's just say we return true if we find it in there, and we return false if we don't find it in there, in the array. Alright, well, this is not too complicated of a function, so we can say, let's just loop through the function. So we're going to say for each value, so for each element or value in array, and I'll try to use the pseudocode that I've used in the insertion sort slides, and that I'll use throughout the rest of the semester. So for val in array, that's kind of like for a Python for loop, so for element in some sequence. If val is equal to the number that we're looking for, then we'll return true. Otherwise, after the for loop, if we've not returned true, we'll return false. So that's going to be our function here. So the first question we should ask is, what is the total running time? And that's a little bit of a trick question because it depends. So if num happens to be the first element in array, well, we don't actually loop through all n elements of array, so it's going to be a constant running time. That's not really a useful thing to think about in terms of comparing this algorithm to another algorithm, because that's just sort of what happens if we get lucky. Well, as computer scientists, we need to be a little pessimistic, and we'll say, well, what happens if we always get sort of the most unlucky set of data that we can get, which means we get all the way down here and we return false. So that's called the worst case. So we'll pretty much always look at worst case analysis or average analysis, but here we'll focus on worst case. We'll look at average case if we're looking at randomized algorithms. So what's our worst case is that we run through all n elements and don't find it and then return false at the end. So let's see here. Let's just go pretty simply here and say that this line of code is going to cost us 1 unit of work. I'm not going to worry about splitting this out and do an actual like while loop and have I equals 0 and do some indexing. That's something that I'll do when I've already got code on the slides, but when I'm handwriting it, we'll take some shortcuts, and that's perfectly fine. Because as you'll see, we'll get rid of constants and leading coefficients anyway, so it doesn't tend to matter that you're perfectly precise on counting up how many lines how many computations are happening on each line. So let's say that for loop line costs us 1 unit of work. Let's say this line costs us 1 unit of work. We do not run the return statement here more than once, so at most that could be 1 unit of work, and we could do that one or we could do this one. So we do both of these for all n elements in the array. So we're going to have 2 lines of code that we run for all n elements, and then we execute one of the 2 return statements. So let's just say the total running time here, so t of n, the total running time of this algorithm based on n, or as a function of n, is 2n plus 1. Alright, so that's the total running time. What is the asymptotic running time? So here's t of n. T of n was 2n plus 1. What's the asymptotic running time? So what we have to do is we have to say, well, t of n has to belong to, and let's just do big O. We'll talk about other types of notation, but now we'll just do sort of the upper bound on the running time, the worst case kind of running time. Well, it's big O of what? So So here would be a good place for you to pause and just see, well, what makes sense to fill in here. Well, if you're lost and you don't have anything to plug in there, that's perfectly fine. If I jump back to this here, this is what we're trying to set up this kind of equation. We're saying that the running time of our function belongs to big O of some other function. We're trying to find f of n, like an appropriate f of n. And there are some systematic ways to do that. But for now, we'll just kind of to look at what our running time is and give a good guess, and then we'll prove that our guess is correct. So if we have our total running time is 2n plus 1, we should look at sort of what's the highest order of n that we find in there, and it's n, n to the first power. So maybe that's a good value for f of n, which means I can plug that into here. So we're going to try to prove that the total running time of our searching an array algorithm is big O of n. Well, to prove that, we have to use this. T of n, we have to find some constant c and some constant n naught where that function holds. So we have to say that T of n is less than or equal to some constant c is less than some constant c times f of n, which we said was just n. And I'll use a little bit of a shortcut notation here. We'll say for all values of n greater than or equal to n naught. So we're saying that this inequality here holds as long as n is greater than some value for n naught. And we'll see that will factor into a few examples we have before, but it doesn't always sort of matter that much. Okay, so what's T of n? T of n is 2n plus 1, and we want to say that's less than c times n for all values of n greater than or equal to n naught. Well, one way to do that is to say that, well, 2n plus 1 is less than or equal to 2n plus n. Okay, so the 2n is equal to the 2n. What we're really saying here is that 1 is less than or equal to n. Well, under what circumstances is that true? So that is true as long as n is greater than or equal to 1. So this inequality here is true as long as n is greater than or equal to 1. So you'll notice that kind of looks like what we have up here. So it turns out for this example we'll have sort of n is equal to n naught will come from that little inequality we had there. And sorry for running out of space here. I'll have to cram in the rest of this example here. So we know that 2n plus 1 is less than or equal to 2n plus n. So that's like saying 3n. And what we really want to show is this one here is less than or equal to c times n. So less than or equal to c times n for all values of n greater than or equal to n naught. Well, what's a value that we can plug in for c to make this right-hand side greater than or equal to the left-hand side? Well, if I cancel out my n's, I can just say that c has to be greater than or equal to 3. So we'll say c is equal to 3, n naught is equal to 1. And now we found values for c and n naught such that this equation here holds.